Hello everyone. I am your friendly community contributor Hasanul Banna Himel. Welcome to our new journey on mathematics for machine learning, where we will be learning all the mathematics needed for our machine learning journey. We will be starting from scratch and let's see till where we go. So, in today's video, we will be covering a few concepts. We will be covering vectors and operations, matrices, systems of linear equations, and finally we will conclude our video with eigenvalue and eigenvectors. And also we will see some my mistake. We will be also work on some code by seeing how these things work in real life. Now let me remove uh, this. Okay, so now at first what we'll be doing is we will be learning about vectors and its operations. So if you heard about vector before, or if this is your first time learning about vector, so what is a vector? Like, if we all are curious human beings, so what comes in our mind? We always curious about different things. So if we want to learn about vectors, a vectors is mainly a mathematical object which has at first it has let me just yeah it has a magnitude, it has a magnitude, also the length, and it has a direction. So if we represent it as an ordered list of numbers of components in a coordinate system, like if we want to write it like let's say we have our v, let's say it is a vector. Here I have let's say in a matrix we have from v1, v2, v3 dot dot and finally vn. So this is our vector of matrices. It is in coordinate system, which is a real number, which is a real number. Now if we want to see like if we want to see something like let's say for example, if we want to see there are different kinds of vectors, like we have our 2D vector and also we have our 3D vector. So what is a 2D vector? 2D vector is most likely in two-dimensional space. Also like let's say a vector in two-dimensional space, let's say 1 and 2. And 3D vector we all can understand by if 2D vector is a two-dimensional space, 3D vector will be a three-dimensional space. Our 3D vector will be represented in like 1, 2 and 3, something like that. It can be any values, like it can be 4, 5, 6, it can be a negative value, it can be anything. Now if we come into the operations of the vectors, we learn about the basic things about vectors. Now if we come to the vector operations, we have a few operations in our vector, like we will be covering the additions, we're going to cover the additions, we will be covering the scalar multiplication, then we will be covering the dot product, we are going to cover the dot product, or also called the inner product, and this is it. Like these things we will be the operations. Also, one thing we will be covering, the norms. Okay, so now if we start, uh, let's say what is addition, the vector addition. The vector addition is something like the matrix addition. If we learn, we will be also covering this in next few minutes. Let's assume we have two vectors. Let's say we have vector A and we have our vector B. Let's imagine our vector A is something like let's say our here we have our A1 and here we have our A2, and in the B vector we have our B1 and B2. Now if we want to addition these two things, it will work something like our first element will be added with our second vector's first element, and our first vector's second element will be added with our second vector's second element. It's something like a vector plus b vector will be addition. It will be worked like a1 plus b1 and a2 plus b2. You can do this with values too, like if I want to, let's say I want to change this a1 b1 a2 b2. Let's assume a1 will be 1, a2 will be let's say 3, our b1 is 5, and let's say our b2 is 7. Now if we want to add, it will be something like 1 plus 5 and our 3 plus 7. Our final value will be 6 over 6 and our 10. So this is our vector addition. Now comes our second part, our scalar multiplication. Now if we see our scalar multiplication here, our scalar multiplication. So in the scalar multiplication, it is something like a number or a scalar value stretches or shrinks the vector. Let's say we all know what is a scalar value, right? A scalar value is a value that doesn't have any direction. Like if I say a is a vector, what makes a thing a vector? It has a magnitude. Let's say if I want to describe this with a direction, let's say 5 meters west. Here you can see I have given a magnitude, and I have given a direction too. Here I am saying someone like you need to find this store, you need to go 5 meters west from here. That is a vector value. And what becomes a scalar value? A scalar value will be something like let's say just 5 meters. It will have just the magnitude. So here for the scalar multiplication, we will be do something like let's say we will be k multiplying an vector. It will be multiply something like k. Let's say our a vector is here. In a vector we have a1 and a2. If I multiply this with k, my k is a simple any magnitude without any direction, so it will be multiplied in ka1 with ka2. Let's say for another example, let's say I have the value of a1 of, let's say, 5, our a2 for, let's say, 10, and for the k, let's say, for the scalar element we have, let's say, 5. So for this one we will be multiplying my 5 with the a vector. So if we multiply this, it will be 5 multiplied, my bad, it will be 5 multiplied with 5 and 5 multiplied with 10. So it will be 25 and 50. So this is how a scalar multiplication is done. Another things, just let me just erase it. So okay, just, yeah, okay. So let's say if let's imagine if our k is greater than 1, it will be stretching our vector, it will stretch. And let's say if my k is somewhat between 0 and 1, what it will do is it will shrink. And finally, if my k is less than 0, or what we call is a negative value, it will flip the direction. It will flip the direction. So that was our scalar multiplication. Now it's time for our dot product or the inner product. Now time for our dot product, also the inner product. So if I want to do a dot product, let's say a vector dot b vector, it will multiply something in this way. It will a1 b1 plus a2 b2 plus a3 b3 plus it will be adding like an bn, like the last number of my vector. So it's also written in this way, like it's also written in this way. Let's say a vector and b vector. If I do the dot vector, we will do the values of a and b vector, and we will be multiplying this our theta of our cos theta of our the vector difference. So now comes the part, like if the result is what, or what is the result indicate in which terms, like what is this and what is that. Now if the result, at first let me erase it. Okay, if you have any questions regarding anything, you can drop down into the comment, like I will try to clarify your doubts. Now let's say if the result if the result if the result the result the result is, let's say, greater than 0, it will be an acute angle. Let's say if the result is equal 0, it is an orthogonal, or it is perpendicular with one another. And if it's smaller than 0, it is an obtuse angle. It is an obtuse angle. So that was our dot product. Now comes part of our norm. Now we will be covering the norm. So what is norm? Mainly this is the Euclidean distance. Let's say we have seen this one, right? And the a vector for our dot product. So how this actually works? This mainly it has its own formulas, right? Let's say if I have an vector v and I am finding the norm, it will be something like the square root of, let's say, v1 square plus v2 square plus v3 square until my v of n squared. So what is this? This is the Euclidean distance from the origin towards our point of v. So now comes the part, like you will ask, like Himmel, why I will be studying this, like is this really important for machine learning? Now comes the part why these vectors and its operations are important for machine learning. We will be covering a few things, like we have, if we want to work with data points, if I want to work with data points, we need vectors. If you want to find the dot products, for the dot product, let's say for the dot product, it will be used in similarity, and also the norm is used in the L2 regularization, and finally the unit vectors. Unit vectors are normally used in the normalized inputs. So this was our vectors and operations. Now if I want to delete all this, yeah, now what are we going to cover is, now we are going to cover the matrices, our second part. For our this content, our day 1, we will be covering the matrices. Now comes the question, what is a matrix? Now let's imagine I have an 2D array or two-dimensional. A matrix is normally a 2D array of numbers arranged in row and columns. You have already seen earlier, right? Let's say A1, A2, A3 and A4. This is a 2 by 2 matrix, right? So this is a 2D array where the numbers are arranged in the rows and columns, and here the, let's say in our machine learning or how this works, it in the rows it is something like the observations or the data points, and the columns is something like the features. Why I am doing, yeah, the features, or also like the variables. So now also we will be covering some simple things, like let's say the matrix operations. We have the addition here, it is something like a plus b. Let's say I have a matrix A of a1, a a2, a3 and a4. It will be, let's say I want to add with b1, b2, b3 and b4. Now if I want to add this, it will work like a1 plus b1, a2 plus b2, a3 plus b3 and a4 plus b4. So this is how the matrix operation, matrix addition works. Now comes our next part, the matrix multiplication. Or yeah, at first let's do the matrix multiplication, then we will be doing the scalar multiplication. Now if I do the matrix multiplication, it is one of the interesting to me. Like let's say I have a matrix. Let's say I have a1, a2, a3 and a4, and I have another one. Let's say b of a1, sorry, my bad, b1, b2, b3 and finally b4. Now if I want to do the matrix multiplication, it will be multiplying in this way. The rows will be multiplied with the columns. Now if I want to like write this, it will be something like the, let's say here I in the a, let's say a is a, let's say, real number of matrix with m and n, and my b is a matrix with the real number of, let's say, n and p. If I multiply a and b matrix, it will be, my a and b will be the real number of m and p. Like I can have various dimensions of matrix, right? So when I'm doing this, my rows and its columns number will be same. Also one thing is, like, one thing to remember, the a multiplied b never will be equal of b multiplied a. Like in the previous classes we have learned, in the linear algebra we have learned 3 multiplied by 5 is always equals to 5 multiplied by 3. But in this scenario, the matrix multiplication a multiplied by b is never equal to b multiplied by a. There can be different kinds of scenarios. You can show me different kinds of scenarios, right? Like there can be scenarios where a multiplied by b can be equal to b multiplied by a, but in the generic scenario you won't never ever see a these kinds of, like these kinds of scenario. So now let's move on. Yeah, so now, yeah, this was the parts of matrix. Now comes like the systems of linear equations. The systems of linear equation. So now what is it? A system of equations that can be written in a matrix form, something like a x vector is like the b vector. Like, so what is it? Like you can, like, you will say like what is this, man? Like what is a, what is x and what is b? You are not defining anything. Now if I want to say like here the a is my coefficient matrix, coefficient matrix, my x vector here is my unknown variable. I'm doing too much errors. So the b vector is our output vector here. So if we want to see some examples, if I show you some examples here, let's say example of, let's say we have equation of, let's say 2x plus y is equals to 5, and let's say x minus y is equals to 1. So here we have two equations. If I want to work with it here, let's say I want to differentiate the coefficient matrix. For here I have 2, here I have 1 with y, and for the second equation in x I have 1, and in y I have negative 1. And then we have our unknown variables, our x and y, and then we have our output vector, our 5 and 1. Now it has some various solving methods, like if I show you, let's say, let's remove this at first. There are few solving methods, like there are the substitution or the elimination method. Then we have the Gaussian elimination, and finally we can solve this with our matrix inversion. So how these things, or where we will use these things, like it is, the substitution or elimination is best for the small systems. The Gaussian elimination is used mostly to convert the matrix to row echelon form and solve via the back substitution. And the matrix inversion, like it is like if the A is invertible, it is something like our x vector will be A inverse and B vector. So thus we can solve this. Now we have a few conditions here to find the solutions, like let me erase this. So for the solution we have something like the unique solution. If I have a unique solution, it will be a full rank. If I do the infinite solution, I will be having some dependent equation, and finally if you found no solution, it means there it is an inconsistent system. Now, in the machine learning, we use this mostly in the like the linear regression models. If you work with the linear regression models, we will be using these things like there will be like this there will be an equation like to solve this, like w will be equal the x transpose x, and we have our inverse of x transpose of y. Now if we want to look at the eigenvalues and eigenvectors, let's say the eigenvalues and the eigenvectors, if we want to cover our final concepts, the eigenvalues and our eigenvectors. For this, let's say like what is eigenvalue and eigenvector. Let's say like for a matrix, let's say for a matrix A, we have let's say it is a real number of matrix, something like n multiplied by n, or also called a square matrix, where it we have a non-zero vector of, let's say, v is an eigenvector if our a of v is equal our lambda of our v. Now here our lambda is our eigenvalue and our v vector is here our eigenvector. Now what does this mean? This means applying a to v vector only scales it. It doesn't change the direction. Now how can we find, let's say to start from, let's say we have our a v vector is equal our lambda v vector. It will be giving us the, let's say if we have our vector in common, I have a minus lambda I of vector will be 0. To find the non-trivial vector, what we need is we need the determinant of a minus lambda I, or for your information, what is I here is an identity matrix, is equals to 0. This gives us the eigenvalue here. Now then we need to substitute our lambda back into a minus our lambda I v equals 0 to find the v. Now if we want to, let's say we want to solve an equation to learn it properly, if we see an problem, solving an problem here, example, let's say we have our a vector, which is let's say we have 2 0 0 and 3, and the eigenvalues let's say my lambda 1 is 2 and my lambda 2 is 3. Now to find the eigenvectors, we will do for the lambda, let's say lambda is equal to 2, the v1 v1 vector will be my 1 and 0, and if my lambda is equals to 3, we will be have an vector of our 0 and 1. Now, why actually this matters? The eigenvectors point are the invariant directions, and the eigenvalues tell us how much those directions are stretched or compressed. Now, this was our the examples, like the explanation or the basic definitions of these things: the matrix, the vectors, the systems, and finally the eigenvalues and the eigenvectors. Now, if we want to look at our the Colab file, I will share this with you in the comment or in the description. Now, here we can see we have a Colab file. At first, what are we seeing here is we are importing our NumPy. I have commented like everything for you for the better understanding. Like here, we are defining two vectors in A and in B. Here, the A plus is showing the addition of our A plus B, and here it is showing the scalar multiplication, like the scalar with our vector. And in this line we're watching the dot product, then the norm, and here how did we find the norm is in the Euclidean norm, like the formula we have seen. Here what we have used in the for here we have A of our 2 and 3. Now for this we have used like let's say this is a vector. It is used in the 2 square plus 3 square, and finally the root 13, and the value will be something around 3.6 and some other values. So after that we will be returning our all the values here. Here you can see that 3.605 and other stuff. Now here in the matrices, here you can see we are at the first defining two matrices, our A and B. We are using NumPy again. Then we added the matrix addition. We are doing the element wise addition here. Then the scalar multiplication. Then we did the matrix multiplication. Then we did the transpose of a matrix, like it is like the reverse of our matrix. The rows becomes columns and the columns becomes our rows, and finally the identity matrix and its multiplication. Now for our systems of linear equations, here we have two equations here for an array A and B. It represents our systems of linear equations. Then we use NumPy to solve our Ax is equal B. It internally performs the Gaussian elimination or the LU decomposition. Now it returns the x, or in 2D form, like we have some value x and y. And finally, in the eigenvalues and eigenvectors, at first we define a square matrix in this line, you can see. Then we do compute the eigenvalues and eigenvectors. So in this line, the np.linalg.eig, this returns our eigenvalues, our lambda 1, which is equals to 2, and lambda 2 is equals to 3, and the eigenvectors corresponding the unit vectors. And finally, the eigenvalues and eigenvectors displays both the eigenvalues and their associated eigenvectors. So that was it. In today's video, we have learned about the vectors and its operations, the matrices, the systems of linear equations, and eigenvalues and eigenvectors. If you have any questions, you can write down in the comment section. I will try to reply all of your comments. Thank you so much for your attention. See you in the next video.